A rope snaps through the air. The ocean rises and falls along a shoreline. A speaker vibrates, filling a room with music. At first glance, these seem like different phenomena, but beneath them all lies the same principle: waves. Motion traveling through space and matter, carrying energy without permanently carrying the material itself. This is Mattermosaic, piecing together the universe, one discovery at a time. Today, we explore waves, frequency, and amplitude, and how these simple ideas shape light, sound, oceans, and even the fabric of space itself. Let's start with a basic definition. A wave is a repeating disturbance that transfers energy from one point to another. Think about it like a message being passed down a line of people holding hands. The first person squeezes the hand of the next, who then squeezes the next, and so on. The squeeze, the energy, travels down the line, but each person stays in their spot. That's exactly how mechanical waves, like water waves or sound waves, work. The particles of the medium, whether it's water or air, oscillate around their original positions. The medium itself doesn't travel across the room or the ocean. Instead, the energy passes right through it. If you flick one end of a stretched rope, you'll see the pulse move forward, but each little fiber of the rope just moves up and down before settling back into place. For centuries, we thought waves needed a medium to travel through. But then came a revolution in our understanding of light. In the 17th century, the brilliant Dutch scientist Christiaan Huygens proposed that light itself behaves as a wave. This was a radical idea at the time. Over a century later, in the 1800s, James Clerk Maxwell unified the seemingly separate forces of electricity and magnetism. His groundbreaking equations showed that they were two sides of the same coin, and that together they formed electromagnetic waves. Maxwell proved that light is an oscillation of electric and magnetic fields, a wave that needs no medium to travel. It can soar through the absolute emptiness of space. This discovery opened our eyes to the fact that waves are not limited to the tangible world of water and sound. They are a fundamental part of the universe's machinery. So, how do we describe these universal phenomena? To really understand waves, we need to focus on two key properties: frequency and amplitude. Frequency is all about timing. It describes how often a wave repeats itself in a given period. We measure it in Hertz, a unit named after Heinrich Hertz, the physicist who, in 1887, experimentally confirmed Maxwell's theory of electromagnetic waves. A frequency of 1 Hertz means one complete wave cycle happens every second. Frequency is what gives waves their unique character in different contexts. When it comes to sound, frequency determines pitch. A high-frequency vibration, like a violin string buzzing rapidly, produces a high-pitched note. A low-frequency vibration, like a deep bass drum, creates a low note. In the world of light, frequency determines color. Red light, at one end of the visible spectrum, has a lower frequency than blue or violet light at the other end. So, when you see a rainbow, you're actually seeing light sorted by its frequency. Next up is amplitude. If frequency is about how often a wave oscillates, amplitude is about how much. It measures the height or strength of a wave, its maximum displacement from its resting position. In sound, amplitude corresponds directly to loudness. A whisper creates small pressure variations in the air, low amplitude. A shout creates large pressure variations, high amplitude. For water waves, it's pretty intuitive. Higher amplitude means taller waves, bigger crests, and more powerful surf. And for those electromagnetic waves we talked about, like light, amplitude relates to brightness or intensity. A dim light has low amplitude waves, while a bright, dazzling light has high amplitude waves. These two properties, frequency and amplitude, work together with a third, wavelength. Wavelength is the physical distance between two repeating points on a wave, like from one crest to the next. Frequency and wavelength are intrinsically linked through the wave's speed. Imagine a road where cars are moving at a constant speed. If cars pass a certain point very frequently, they must be spaced closer together. It's the same with waves. For example, in air at room temperature, Sound travels at a steady speed of about 343 meters per second. If you increase the frequency of the sound, meaning the vibrations are happening faster, the wavelength must decrease to keep that speed constant. The faster the oscillation, the shorter the spacing between the peaks. Now, here's where things get really interesting. What happens when two waves meet? They don't just bounce off each other, they interact. This is a principle called interference. When two waves overlap, their amplitudes simply add together. If the crests of one wave align perfectly with the crests of another, they reinforce each other, creating a much larger wave. This is called constructive interference. It's like two people pushing a swing at the exact right moment to make it go higher. But if the crests of one wave meet the troughs of another, they cancel each other out. This is destructive interference. It's the magic behind noise-canceling headphones. They generate a sound wave that is perfectly out of sync with the incoming background noise, effectively erasing it before it reaches your ears. The beautiful, swirling colors you see in a soap bubble or on an oil slick are also a result of light waves interfering with each other. There's another powerful wave phenomenon called resonance. Resonance happens when a system is pushed at its natural, preferred frequency of vibration. Every object, from a wine glass to a bridge, has certain frequencies at which it will vibrate most strongly. A tuning fork is a perfect example. It hums loudly and clearly only at its specific resonant frequency. Musicians rely on this to create beautiful sounds from guitars, violins, and pianos. But resonance can also be incredibly destructive. The infamous collapse of the Tacoma Narrows Bridge in 1940 is a chilling example. The wind created oscillations that happened to match one of the bridge's resonant frequencies. These small vibrations were amplified over and over again until the structure twisted itself apart. It's a dramatic reminder of just how powerful wave interactions can become. From the gentle swells of the ocean to the radio signals carrying our favorite songs, from the seismic waves of an earthquake to the visible light that lets us see the world. Waves are the universe's primary method for transporting energy. Frequency tells us how rapidly the motion repeats. Amplitude tells us how powerful that motion is. Together, they form a universal language that describes oscillations throughout nature, on every conceivable scale. And when I say every scale, I mean it. The story of waves doesn't stop with bridges and light. It goes all the way down to the subatomic level and all the way up to the cosmic. Modern physics, specifically quantum mechanics, describes fundamental particles like electrons not as tiny solid balls, but as wave functions, waves of probability that define where a particle might be found. The very building blocks of matter have a wave-like nature, and then, looking out at the grandest scales of the cosmos, we find waves there too. In 2015, the LIGO Scientific Collaboration made history by directly detecting gravitational waves for the first time. These are ripples in the very fabric of spacetime, predicted by Einstein a century earlier. The ones we detected were created by two massive black holes spiraling into each other and merging, an event so cataclysmic it sent waves shuddering across the universe. Waves connect the smallest quantum scales to the largest cosmic structures. They reveal a profound truth about our universe: that simple, repeated, structured motion can transport energy and information across air, water, solid ground, and even the vacuum of space. It's a pattern that repeats everywhere, a fundamental piece of the cosmic mosaic. This is Mattermosaic, piecing together the universe, one discovery at a time. If this exploration changed how you see the ripples around and within you, share it with someone curious about the hidden patterns shaping our reality. And let us know in the comments what scientific thread we should follow next. Thanks for watching.